Hi, everybody. Thank you very much for coming out. I know we just had our 15-minute break, so it's really nice to see people starting to come back in for this. My name is Maximilian Riccioli. I'm a third-year undergraduate at the University of Texas at Austin studying electrical engineering.
I'm Michael Gutierrez, sophomore at Caltech. Sophomore at Caltech, Michael Gutierrez, studying astronomy.
And today we'd like to tell you a little bit about this project that we helped to develop at our internship at MIT Haystack Observatory over this summer. Sort of this satellite communications hub built around GNU radio processing. So here's a map of our presentation. We'll be starting at the left. I'll give a little introduction to our satellite mission as a whole. It's a little bit unique in terms of satellite missions, so we'll talk about how that kind of motivated the development of our very general ground station interface here to process for different types of satellite missions. And then about halfway through, we'll switch over to Michael, who will tell you more about the actual GNU radio implementation, the nuts and bolts of this thing. So a little introduction about MIT Haystack Observatory. It's a multidisciplinary research facility, and one of their disciplines that they research is geospace, which very broadly is the study of space weather. So kind of the interactions between the solar wind and the magnetic field and the ionosphere, the atmosphere. Anything above the Earth, not too far away, they'll look at it, right? So one geospace phenomenon that you might be familiar with is the aurora, the northern or southern lights. This is an optical phenomenon which occurs at the poles whenever high energy electrons come in and interact with neutral particles, causing, again, this optical disturbance. This is around 150 kilometers altitude, but if you go up to around 500 kilometers altitude, you'll actually find a radio aurora. So this is interesting, right? Not as many people are familiar with this as the, pretty northern lights, but it's just as real. And we can detect it from the ground on occasion. But what's interesting is that plasma physics and radio propagation theories both predict that this should not be possible at all. It should be completely attenuated by the time it reaches the ground. So MIT Haystack really wants to study these phenomena, because, of course, whenever you have observations that go against what your model predicts, that's where the most interesting science occurs. But part of the issue is that even though we can receive these signals on the ground, a lot of the important characteristic information, like their polarization and their angle that they come from, can get lost or muddied on the way down. So we need a way to more directly observe these radio aurora, which brings us to our satellites, which are planned to go into low Earth orbit. That's between 200 and 2,000 kilometers. And these will be able to get us clear access to observing this radio aurora from the top down, so we can not have it blocked by the atmosphere, basically. In order to do this, and just like I mentioned on that last slide, in order to get this polarization and incidence angle information, we'll be using electromagnetic vector sensors, which very broadly are one element which can discern all 6 dimensions of the electromagnetic field, XYZ electrical, XYZ magnetic. And from this, you can process out polarization and the incidence angle. And this will allow the scientists to test their different theories about how these emissions are created. So Arrow and Vista, that's the name of these satellites. These will be the vessels for these vector sensors. You can see on the little mission patch there, those crosses at the top of each of those satellites, those are the vector sensors. They'll kind of expand out from the satellite. Arrow, just as we discussed, its primary mission is to observe these radio emissions high up in the atmosphere. But Vista is actually an interferometry experiment to hopefully improve the data acquisition of Arrow, which interferometry is a whole entire field of research on its own. But very, very broadly, if you have 2 observers watching the same event, you can more than double the data output or the data resolution from it using interferometry techniques. So these satellites will be performing interferometry in space. It looks like the GIF didn't load, but in the top right, here was, yeah, it's a PDF. This was supposed to show the vector sensor kind of exploding out from the satellite. It's really an engineering marvel that they fit this whole thing into such a small satellite, both of which, Arrow and Vista, are CubeSats, 6U. 1U is 10 centimeters by 10 centimeters by 10 centimeters. So each of these satellites is 6 of those, so 20 by 30 by 60 centimeters. And they fit this whole really like 2 meter by 2 meter antenna into it. It's kind of amazing. Yeah, it's huge. As discussed earlier, we'll be performing interferometry on the experiment, but we need to basically have 6 streams of IQ data coming down from the satellite in order to do that. So that's a huge amount of data that will need to be processed by our ground station, which of course leads us to talking about our ground operations. So for any spacecraft mission, Arrow included, one of the most important tasks is ensuring that you can actually talk to the satellite. Because if you put it up there and you can't speak to it and it can't speak to you, then you've basically spent millions of dollars and thousands of man hours to put space junk in space, right? So we're going to use a ground station. We're going to use MIT's and various other collaborators in order to uplink meaning up from the ground station to the satellite, mostly low volume telemetry data and command data over UHF, which is on the order, as you can see there, of around 10 kilobits per second. And we'll also be downlinking, called that because it goes down from the satellite to the ground station, UHF telemetry data and health data, so letting us know what the satellite is doing at any given time, as well as downlinking over X-band, our experiment data, as discussed before, this IQ data. So fortunately for us, that wasn't really our project. The ground station hardware is pretty well set up as it is. Again, as I said, there's a lot of collaborators on this project, one of whom is Morehead State University. That's one of the primary dishes that we'll be using. It's a 21 meter. And yeah, we'll also be using the 18.6 meter reflector at Haystack, which has its own phased array feed, which has previously been used a lot for radar and satellite tracking. It'll allow us to kind of beamform and track these satellites with greater precision than you could just by angling the antenna. And there's also a cryogenically cooled X-band receiver, which only receives right now because in the past it was used mostly for sort of measurement experiments, again with this geophysics and the other disciplines at Haystack. But hopefully it'll also be transmit by the time that this mission goes into orbit. And all of this feeds into a big stack of EDIS N310s that live down in the server room underneath the ground station. Do you want to?
Oh yeah, I was just gonna highlight that. Is this on? Oh, hello. Yeah, so we have a very diverse array of hardware that we want our software to work with. So that kind of defines, as we'll get into, GNU Radio really helps us to have compatibility for all of these out of the box.
Exactly, yes. One of the reasons why we ended up going with GNU Radio for our ground station interface, we'll talk about this a lot more later, but the hardware that we're using is pretty diverse, and we feel like this could be kind of extended to even more hardware, even outside of what we have. So our second objective then is to have a way of conveniently talking with the spacecraft. A sort of unique problem with low Earth orbit is that your satellite passes are very short. After coming up over the horizon, you can only have between 5 and 15 minutes to actually talk to this thing. So any mistake that you make could also turn it into space junk, right? So it's really unnecessary. It's not the best to have a human doing this within this 5-minute window because you don't want any mistakes to be made. But there's no real solution to this quite yet, it seems. Currently, what mostly happens is you'll either use a bunch of disconnected software in order to facilitate all this. So you'll be copying and pasting values between each window. You can see that on the bottom left there, sort of this one-off solution just for the mission. You can shell out a pretty significant amount of money for a proprietary solution, but other than causing a recurring cost that can actually sort of lock you into using a specific vendor through your whole mission. And it's nice to not have to do that, right? You want flexibility. And if anyone here is familiar with satellite operations, NASA's OpenMCT does support scheduling, but it actually doesn't support any of the radio side. So there's no easily configurable pre-built solutions for this issue, which really brings us to why we were developing the Haystack ground station interface in the first place. So I'll hand it off to Michael here.
Yes, no easily configurable pre-built solutions until now. So this is the Haystack ground station interface, which we're working on. Well, we plan to open source it once we finish developing it, but the idea is that it's human readable and extendable to any satellite mission. So even if they say another university or science team doesn't have our exact satellite hardware, and obviously they won't have access to the specific satellite dish that we do. Actually, the UHF phased array feed that we have, there's only one in the world right now because it was custom built. But yeah, so we are building this, like I said, with GNU Radio at its core because it's very human readable. You can load in, the idea is you load in one configuration file or flow graph or what have you for specific to a satellite, and you can hot swap whatever signal processing and data syncs and sources that you need. So yeah, the critical thing is we want to keep it human readable because yeah, we don't want to, in case there's a contingency or like you need to change something quickly during a satellite pass, you don't want to have to dig through the source code. So I'll give some specific examples of kind of the problems that we were working with in building this software. So one of the most important things is the packet processing, because so this is after you have the radio signals downlinked from the satellite and you've demodulated them into a bit stream. There's a million different ways that you could package those up into a packet where you might have preambles and sync words and data scrambling and error correction and all of this. And there's a huge diversity of those different systems throughout all kinds of different satellites. So, and we want to be able to support all of them with minimal configuration. So first thing we tried was there are some built-in GNU Radio blocks for this. They didn't quite fit our purposes because most of them use tagged streams more like in a synchronous manner. And for ground station operations, it's very much asynchronous because you're not going to have data constantly coming in. It's going to be coming and going. So to that end, we built a bunch of custom blocks that used asynchronous message passing system. So we utilize a lot of tools from the GNU Radio Satellites package by Daniel Esteves, which was really great. And we also built lots of our own custom blocks that are all of them take in one configuration file. In this case, you outline the packet format that you want to decode. So you say, oh, the first 8 bits are the length, and then the next 8 bits are the type field, and et cetera. And yeah, it's much easier than creating, for example, a packet header object in each flow graph custom. So we wanted to abstract it out a little further. So, and we found that the GNU Radio higher block infrastructure is really effective for doing this. So, for example, again, we have one config file. So on the right there, that outlines like pretty much all of the communication parameters for a given satellite. So it's like, oh, we're going to use the UHF radio. This is the sync word, and it's going to use FSK modulation with the frequency offset of this, et cetera. And all you have to do is load it into this one Haystack GSI block, which is part of the out-of-tree module that we're developing. And it will automatically build this entire receive chain for you. So you don't have to click and drag every individual filter and clock sync, et cetera. yeah, so essentially, we're going for user-friendly interactions. Ground station in a box, as the slide says, the user should not have to have really deep signal processing knowledge in order to perform the actual basic functions. But of course, if you do need to change some low-level settings, those are still accessible. And then on the other side of this, so after we've decoded the payloads, we want to, so in AeroVista's case, we want to send it off to a REDIS database so that the science team and the mission ops can access it. So what we had been doing before was using a lot of ZMQ. So we would send all of the byte stream into a ZMQ sync, and then we had to have a Python script that wrapped the entire flow graph to receive from ZMQ and then send off to Redis. And that it had a lot of moving parts. It was very cumbersome, hundreds of lines of code to deal with multiprocessing for different flow graphs, et cetera. But we realized we could just write a custom block to send the byte streams directly to Redis, which simplified things a lot. And it really simplified it a lot in terms of the lines of code. And it's this kind of scheme is really expandable to, it doesn't just have to be Redis. It can be theoretically send data wherever you need to. So that's kind of what we've been working towards. So with an eye to future development, the end goal really is to use the GNU Radio Companion as a user interface, essentially. The visualization is having the ground station operator as like an old-timey telephone switchboard operator. So say you have like science data coming down on the X-Link band. So the operator can connect up the X-Link radio and send it off to the, we're using this packet structure, so we plug it into this demodulator, and then, we want to send this to the science cloud, so we'll plug it into this database sync. And then on the other side, if there's instructions coming in from mission commands, then we can pull from that scheduler database and then put it through the UHF demodulator and send it right back up with minimal configuration of the low-level parameters. So on that note, so Max and I we spent a very large amount of time staring at GNU Radio Companion this summer, 10 weeks, multiple hours a day. So we have developed a few quality of life improvements to GRC as a whole that we hope we can integrate into the main branch at some point. So we added dark mode because, again, 6 hours, 6 to 8 hours of staring at the screen, the white background tends to singe the corneas a little bit. And then also with an eye to accessibility, we added color-coded blocks depending on their function, which really helped read like the functionality at a glance, which is again kind of what we're working towards, the human readability of it all. And then with more towards the functionality end, we want to expand the block user interface a lot because right now it's mostly static. Like you can hide and show some parameters depending on a drop-down, but an example that we were playing with here on the screen is it's a packet parser block that starts out blank. You import a YAML configuration file detailing different packet protocols, and then it'll read that like in compile time basically, and present you with different options based off of that. So yeah, we think it could be a lot more dynamic. So we have some of this stuff implemented in our own GNU Radio branch, but don't actually know how to integrate that with the dev branch. So I'll have to connect with somebody about that. Yeah, so that's about all we have. We just wanted to highlight some resources that we found very helpful. In particular, wanted to give Mark Lichtman a shout out at the AAB booth. His PySDR website was supremely helpful because, I don't know, at least for me, when I was coming in over the summer, I had zero knowledge of DSP. I was opened up GNU Radio and I was like, what is a filter? So that, yeah, we had the PySDR tabs open, I think, probably just the entire summer, like never closed it. So, and then, oh yeah, as I said, Daniel Esteves' GNU Radio Satellites repo and blog were very, very helpful. He integrated a lot of those tools.
Ryan Voles developed Radioconda, which was super useful for us. He was actually one of our mentors at MIT Haystack, so it was really interesting to talk to the guy who made it, and we're also using his package, right? But other than that, I think that's all we really wanted to talk about. So thank you all very, very much for listening to us. And if any of you have questions about sort of the satellites or the ground station or the GNU Radio operation of either of these things, we would love to take them right now.
So, any questions in the room? Yes, the gentleman in beige.
So I've been working with the protocol formatter for quite a bit, and it was one of the most tedious things to work with because they're not all, the blocks aren't compatible with other blocks. So something like the header payload demux did not work as expected, and it took a lot of trial and error to get to something like that. I guess my main question is, what was your experience with those blocks, and more so, how did you replicate them?
Yeah. So like I said, the way we were kind of importing the data was asynchronously. So we had like a USRP source coming in with just the raw modulated data, and I think we used like there's a GR satellites block, which is like sync to bytes sync to PDU, sync to packed PDU, which takes in bytes and then looks for the sync word and then crops it at the appropriate length and sends it off. So we kind of were, by the time we wanted to process the packets, it was already in PDU form. So that was a little bit difficult with the built-in blocks because they pretty much only have support for like, oh, the header is this long, and then you can maybe check the CRC. But we wanted to add support, like easily configurable support, like all using the same block for as many different protocols as we could. So yeah, that was the main motivation behind not using the built-in blocks.
So before we continue with in-house questions, there's an out-of-house question that asks, like, what's the advantage of REDIS, of using REDIS in your setup, seeing that this is like another message distribution thing?
Yeah, sorry, I didn't hear all the questions.
Sorry, seeing that Redis kind of is also distributing messages and state and stuff.
Oh, why did we use Redis? Yeah, so actually I can go back to the other slide, the diagram. So this is kind of like the whole overview of the entire project, and we really worked mostly on just the little GNU radio box down in the bottom. But the Redis server is kind of what's going to connect the ground station to everything else. So we're going to load all of the, for example, the telemetry and health data into NASA OpenMCT. Oh yeah.
No, keep going, sorry.
Oh, I guess there's also two microphones. Yeah. And then we're the Redis server also is going to interface with like the file transfer function. So if we need to upload like new firmware or whatever up to the satellite, then that'll also go through the Redis. And also for like any automated mission control software, like for example, we use Nano MCS from Nano Avionics because that's what the Aero and Vista satellites are use Nano Avionics M6P buses. So we can also hook that up directly to, well, almost directly to Redis.
And a lot of the specific motivation for using Redis was to be able to kind of dump in commands onto a Redis sort of receive stream, which would be picked up by this ground station software transmitted. And then at some other point, it would dump in these received commands back into a Redis downlink stream. So the point of Redis was to make this asynchronous and also able to be accessed from different locations, sort of, so that way our partners, you know, at Moorhead, thank you very much, excuse me, at Moorhead could interface with it and perhaps, you know, transmit, get things ready to transmit over our dish as opposed to their own, right? So just kind of distributing this, it made it was a lot easier using Redis.
Okay, thanks. Then there was an in-house question, I think here somewhere.
When's your launch date?
That's a good question.
I believe it's 2024 or 3. I don't exactly remember. I'm sorry.
Well, theoretically, this will be done before that because we're also going to be using at least the ground station at Haystack to track other satellites. Yeah, we think it's going to be like a backup center for NASA because we got like a NASA SDR set up in there also. So,
So Derek actually asked, said that your YAML format for like the form, like your YAML definition looks like it has a lot of overlap with, you know, SAT YAML from other projects. Is there like some advantage to maybe, you know, coordinate and merge these formats?
definitely, yeah. Actually, I mean, I started writing a lot of this code as like within the GR satellites package actually, and then it got too different, so I didn't turn it into another entry module. But definitely, definitely a lot of this is reliant on other packages, and would definitely love to, yeah, combine efforts.
Okay, is there another question in the house? Then we have a time for a question online, and it's been asked whether like there's a lot of overlap with what SatNox basically does as a distributed array of satellite ground stations. Do you feel like you reinvented the wheel a bit out of necessity, or is that just intentional, or are you doing something different?
Sorry, I'm having trouble here.
Yeah.
Okay, sorry, that's sorry. There was a question whether you're not replicating the effort that SatNox does, basically, and whether you feel that's intentional or necessary, or just too separate a problem to solve.
Yeah, SatNogs definitely is a really great program. So we also, in this presentation, we focused a lot on the receive side, but just as important is going to be the transmitting side going back up, which I don't think SatNogs does. So yeah, we want to be able to transmit commands. And
really a huge focus of this project is getting the infrastructure in place to be able to transmit. So that's a really huge consideration and also a really huge reason why we built a lot of it in GNU Radio.
Okay, cool. Is there another question? Otherwise, I'd say we give the speakers a big round of applause again because, you know, students.